So our next group is is a project, currently supervised by our external collaborator, Dr. Chris Hendricks. I just saw him in the audience. Thank you for joining. And he's from our partner, the Naval Surface Warfare Center at Bethesda, Maryland, actually very close to us. And this year, he helped supervise this project to redesign a pressure and temperature monitoring device for the lithium-ion battery. He and his group are working on this at Naval Surface Warfare Center. And the students who work on this project are Jenna and Samba. So they have already shared their screen. So Jenna, Samba, if you're ready, you can go ahead, introduce your project.
Okay, thank you very much, Dr. Shu. Can everyone hear me okay?
Yes.
Okay, so good morning, everyone. Thank you for being here. So we are the lithium-ion battery group. My name is Jana, my partner is Samba, and we will be presenting our project for the redesign of a pressure temperature monitoring device for the lithium-ion battery. So as an overview of this presentation, we will discuss a brief introduction about lithium-ion batteries along with our existing design. We will discuss the scope of study, how we approach this problem along with our Gantt chart. The conceptual designs we will introduce and with the the puncturing mechanism as well. Our creole designs, we will show how we drew this out, how the prototype came to be along with the final product that we have now. The testing we will show closer to the end along with our future work, our conclusion, and all our acknowledgments. So as an introduction for this project, everyone knows, or majority knows, lithium-ion batteries. So we know that electronics in our daily lives, we want to carry them around, everywhere. So they obviously need charge. So that's where portable devices like these batteries come into play. So lithium-ion batteries, they are the majority used rechargeable batteries in the market. So they help charge our phones, our laptops, cameras, etc. So the lithium-ion batteries, the fact that there's still so much room for improvements, that's where our project comes in. So as an example, to make them last longer or to make them safer to use. So in this presentation in our project, we wanted to build a test chamber that would allow us to monitor both the generated gases from the pressure of the puncture as well as the temperature of the lithium-ion battery while being cycled under different conditions. And this helped us gain a better understanding of how the failure mechanisms goes on internally in the lithium-ion batteries. So reiterating once again, the existing design, most of you remember this picture. So this is where we are based off our conceptual designs. Here in the existing design, we have the two top and bottom end caps. These are made of stainless steel. They're used to cycle the battery. The two O-rings, top and bottom, that is used to help seal the chamber. PTFE cylinder here in white, that is to reduce the heat transfer away from the battery. The thermocouples here, they are to read the temperature of the battery. Puncturing needle is up here up top. It will be here. It is puncturing the top of the battery, if you can see. Pressure transducer to the right to analyze the internal gases, and the gas port to vacuum the test chamber. So our scope of study, this is where we based off our planned improvements. So to begin, we wanted to minimize the free volume that we get from the pressure transducer to get more accurate pressure readings. That's one. We also wanted to reduce the amount of heat loss from away from the battery. In this was the big one. We wanted to automate the pressure, the puncture mechanism. So going from a manual to some type of automated process. The puncture of the battery wanted to switch the location so that the from the negative to the positive, from the positive to the negative, I'm sorry, so that the pressure release valve that you see at the top, the bubble, that would remain intact. It would be undamaged. Lastly, we wanted to add a temperature monitoring system that would go along with the thermocouples. So that way, as the thermocouples would read the top, the middle, and the bottom,
Hello.
the added monitoring system would read at
Hello.
any point around the battery. So introducing our first
Hello.
conceptual design, we have this lovely image right here. To clarify, this is the pressure transducer. Here we have the gas ports to collect and encase the test chamber in vacuum. Puncturing needle at the top, the top and bottom end caps, and here would be the
Hello.
PTFE cylinder, along with the pins that would hold down
Yeah.
the chamber. As here in the exploded view, we see a little bit more. Here we have the seals to help vacuum the chamber, um,
For what?
any charging ports that would add as extra to cycle the battery. The battery here is in red. In this design,
Which video?
we
Okay.
were able to
Which
switch the
video?
battery so that the new location of puncture would avoid the pressure release valve, so from the negative to the positive. And this design
I
also
give
limited dead space,
I give you
so it
one
would lead to
yesterday,
more
right?
accurate
Last
pressure
night.
readings, hence this chamber, which would automatically, the puncture would happen and automatically go to the pressure
Oh,
transducer.
okay. Call
The
me right back.
We consider the PTFE cylinder to stay for better insulation to minimize the heat transfer away from the cell. And we also this design also created will be created in vacuum. So before any puncturing of the cell, it would eliminate any potential contamination from the outside. This design we considered to have too many parts. It was very complex in a way to build it. So that was a con about this. Also, we wanted to attempt to 3D print the end caps as the existing design had, but due to the inavailability of the metal 3D printer as well as training, that was a limit that limited us. For our second conceptual design, here this is the exploded view. Here the is very similar to the first and also the existing design. The main difference you can see here would be the coupling. This coupler is a pretty much a hollow adapter that would connect the puncturing needle as well as the pressure transducer. So this would minimize the majority of the free volume that we would get from adding that pressure transducer to the puncturing needle. Here in the battery in red, you kind of see the tip. So this design also reversed the puncturing location to maintain the integrity of the pressure release valve. Also here it was a lot more simpler parts than the first design. Although as the first and second ones they have these pins that would help seal the chest chamber. So these pins would automatically limit us to having a automated puncturing mechanism. So that was a con about this. It would still be a manual process. Bringing up the puncturing mechanism, this is where our third design comes in. It is a pretty much a compilation of both designs. So this way, the puncturing needle and the adapter are the puncturing needle and the pressure transducer are adapted. They're connected pretty much through the end cap you see at the top, instead of having the coupler. Instead of the PTFE cylinder that the previous design used for heat insulation, we decided to go with glass cylinders. This way, the addition to the thermocouples, the temperature monitoring system, we would be able to use a pyrometer, which is an infrared thermometer. It would go through the glass and read the battery at any point. Also, this design also was considered to have less parts, so we could order in a calm manner, and it wouldn't limit us at all. And also, as I said before, this design would lead to an automated puncturing process. So going in a little more to the materials here, the glass cylinders, we have an inner one and an outer one. The inner one, well, the the material for these glasses, we decided to go with borosilicate glass. This type of glass, you can think of it as Pyrex glass if you don't know what it is. So this, we considered it because the thermal expansion coefficient was relatively low. So this meant that, Pyrex glass, it would going from a cold to a hot temperature, it wouldn't shatter, it wouldn't break. So it was very safe for us to use. Just when, if you were cycling the battery, the battery would heat up. So that was a consideration that we went through. For the puncturing needle, this is our initial thought. I'm pretty sure most of you have seen this at the doctor's office when they draw blood or so on. And so the tip here, that is the part used to puncture the needle, the battery. And then the internal gases that would appear from the puncture would travel up the tube. And since the needle is connected directly to the pressure transducer here, that's where we would get the most accurate readings. Lastly, introducing our puncturing mechanism here, we see our thought process was to use a linear actuator. So, the engineering department, the students, you would see these actuators in the Luzbot 3D printers, as the previous project discussed. So, how these linear actuators run is basically through a type of motor, stepper motor, which you can see to the left here. These motors are run by some type of microcontroller. In this case, we used Arduino, and this is the driver that would control the positioning of the black box that you see right here. This is connected to the top end cap, which would raise and lower the entire top system in order to puncture the battery. This we will see in the following next slides. So Samba will now talk about the prototype.
All right, thank you, Jana. And hello, everyone. Thanks for taking the time. Thanks for being here. So
Okay.
now that we have a pretty good idea of what we want to do, it was time to turn to Creole and draw our end caps. And this is the negative end cap. And when I
Yeah,
mention
I did
negative end
listen.
cap, I'm
I
referring to
recording
the
it.
top end cap. And this is what it looks like when printed. So we did the drawing with the different dimensions. And
I don't
what you
have the
can
other
see
one yet
here
because
is
I
the
saw the email.
ports where
The
one
person
will
say
be
will send you
for the
later. Like,
cord to charge the battery, and the
yeah.
other port will be to collect the gases. Moving on to the positive end cap, and again, the positive end cap is the bottom end cap here, and these are the different
You send no
dimensions. Two
information.
ports, one for the port to cycle the battery to charge it, and the other port
No.
for our thermocouples. And here, this is where your outer cylinder will be sitting, then
They
your
have
inner
one will be
cylinder, then the
sending
battery.
out today, sometime today, later today.
So when it is fully assembled, we
For
did a creole design, so we can just have a
the
pretty good
the
idea.
person you
So
asked for
basically, you have your two linear
this morning.
actuators.
You
On the
send for
top,
one
your stepper
person, right?
motors, and connected to those linear actuators, you have that top
Yeah.
end cap
One of
with
them
the
respond
pressure
already.
transducer. So this goes up and down, and when it goes down, it will
Yeah.
puncture our
We give
battery
it to
and
you
keep the
later.
chamber sealed closed. And this is an
Yeah.
exploded view with all the different components. Now, we moved on to the next phase of our project, which
Yeah.
was to do the prototype building.
I just wait a little
And
bit.
what
That's
we
all.
did, we used 3D printing. We used the TAS printers. So here
Yeah, I
you're
can show
looking
me the
at
video.
the end caps in the process of
Let
being
me see. I
printed.
can access to it.
Then this is the finished product. Now it was
I
time
already
to
sent it.
put it together. Here in this
Which
picture, you
video?
see the end cap connected to the puncturing needle. And then on this picture, that's the other side of the end cap where you have the
Yeah.
pressure transducer
With the
connected
student,
to the
I
end
didn't
cap.
finish yet.
And still
I
going
didn't
on
start
with
that
the
one yet.
prototype, putting it together. This is the thermocouples, putting the cylinders inner and outer. And when fully assembled, this is what it looks like.
Hmm?
And again, we did a prototype so we can make adjustment and
I didn't do
be able to
anything yet.
finalize our product, the final
I
test
didn't
chamber,
starting yet. I watching
which
the
was time to
event a
go
little
ahead
bit.
and build it. Here,
It doesn't take me long.
I don't know how clear this picture is, but pretty much you're looking at the end cap
Don't worry.
inside the printer while it's
It
being
doesn't take
printed.
me long. I thought the other person will
And
be
this
saying
is a
soon
better
so that
view
I
of it
can do
where
one
the end cap
together.
is done, ready, and is sitting and drying off.
Yeah.
Um, Now, I'm not, you're looking at these pictures here. I'm not sure how familiar you guys are with the 3D printing, but one issue that we found is when you're
Okay.
making holes,
I call you.
like let's say the pressure transducer needed to be connected to the top end cap, you will make your holes get the right dimensions, but when you print it, depending on the material, it might expand or contract. So the size of the hole will not be what you wanted. So to avoid that, we made this little block here with different sizes so we can get the right one. And this was for the pressure transducer. This is for the valve. And we also built a leg so our linear actuator could be standing up.
Special service. Video
And
presentation
the
delivery.
entire system here is what
Okay.
you're looking at when it's fully
Dealing with
assembled, where we have
boxes.
our setup, our power sources, the laptop with the codes, the
Graduation.
two linear actuators with the stepper motors on the top connected to our end cap, the outer inner cylinder, our valve, the legs, and this is another view of the
Okay,
system.
new file.
Now that our test chamber is done, time to test it and see if it actually does what we wanted it to do. So we first started to test the puncturing mechanism. So what you're looking at here is the top view of an empty shell of an 18650 lithium ion battery. So it is not a live battery, it's just the empty shell. Now, two problems, two issues when we try to puncture this
Box
battery.
one.
One, the puncture is not centered, it's on the side. And the other thing, more important, we could not puncture the battery. It didn't work. So we made some adjustment and try again.
Student
This
visa.
time we got a puncture,
Graduation.
but it wasn't centered. And the reason why we want the puncture to be centered, there is a jelly roll on the outside, and you do not want to hit that because if you do, you will short circuit the real battery. So we tried again with some adjustment, a little better,
Okay.
but still not where we wanted. And there was another issue that was coming up. What you're looking at here is a picture on the left of a new needle, a puncturing needle, the new one.
I don't have time for
But
that.
when we try to do the punctures, this is what was happening. Our needle will bend.
Okay.
Why? Because the battery was not standing still, it would be moving. So we needed to fix those issues. We put our engineering cap on, try, and then this is what we did. What you're looking at here on the left picture is uh, the cap of a bottle that we also put a hole in it and then added it inside our inner cylinder to stabilize the battery. Then we try to puncture the battery one more time. And I will let you watch this short video and see what happened when we tried.
Okay. Computer science. Oh, something. Missing. Engineering ambassador. Engineering ambassador.
Right.
Can do
And
that.
that sound you heard was the battery cracking. And finally, we were able to puncture it just where we wanted, center. So the next thing that we tested was the thermocouples. We wanted to see if we were getting temperature readings. So our setup was
Reset.
um,
Change.
we use a resistor,
Reset.
330 ohm was the rating that we connected to a voltage source. So basically, what we were doing was increasing the voltage across that resistor to see to measure the temperature on the actual resistance. And what we did was what we found out. We started at temperature, room temperature, and this is in Fahrenheit, by the way. So this was room temperature, and we were able to get all the way to 200 degrees Fahrenheit. And we could have gone even higher, but as you can see on the pictures here on the right, the resistance was starting to melt. But we were able to get our readings, so our thermocouples did work. Now, some few notes here.
Continue
Um,
ambassador.
in the beginning of a project, we set out to have a vacuum seal. We wanted our test chamber to be sealed.
Continue
Unfortunately,
ambassador.
we were not able to get that. We got close, but we couldn't get it completely sealed.
Creole.
The reason being, one, was that when the resin cure, the surface of it is very rough. So that was one reason. Even though we were trying to use O-rings, we could not fill all the gaps with the O-rings. So maybe one thing that we should have done was smooth up the surface using sandpaper or something like that. And the other issue also was the O-rings that we were using. They were they were not the right size. It was hard to find the exact match for our cylinders. So next note here is the inner cylinder.
Gender.
Again, when you have your project, you have your ideas. This is how you want to go. This is the type of material you want to go with. What we find out was
Gender.
going with glass was kind of was not the good choice because if you wanted to cut the inner
Foundation.
cylinder to the right size, you would not get a smooth cut on the glass. So we found a better material, which is polycarbonate. It's just like acrylic,
Show
but
Henderson.
it's stronger, has a higher melting temperature, and also cutting it for our purpose will give us a smooth cut, no breaks. And lastly, the IR thermometer, the pyrometer, the device that we try to use to measure the temperature, which the pyrometer did not work, wasn't working correctly. So the data that we got from it was not usable. Now, in conclusion, this whole process really we're trying to improve on lithium ion batteries. And one way to do that is to understand their failure mechanism.
Show
So
Henderson.
the studying the correlation between the failure mechanism and the
Show
inner
Henderson.
gas's pressure, along with the temperature change during different cycling conditions, can be a beginning of a solution. Like can be a beginning of answering those questions if we can find the correlation. And the device that we worked on and improve is really a key tool that can be used to get those answers. Now, in finishing this presentation, I just want to acknowledge a few people, and I will actually start with my partner, Jana. I just want to take a minute to say thank you, Jana. Thanks for the hard work, and this was really and truly teamwork. You really made it. You really made it fun. Thank you. Also, want to thank Dr. Shu for being our main advisor and mainly making this process go as smooth as possible, making the materials available to us in a timely manner. Next, uh, Dr. Hendricks from the Naval Surface Warfare, the Carrock Division. Thanks for all the advice. I mean, you gave us so much. Actually, you told us not what not to do and also pointed us to the right direction. Thank you so much for all the advices. Uh, Thanks to Dr. Shady. Thanks to Dr. Osasanya. And on a more personal level, all of this would not be possible if it wasn't for Dr. Klein. So thank you. Thank you so much, Dr. Klein. And lastly, want to thank one of my classmates, Jaime Rios. Thanks for the training on the 3D printers. I mean, you're the man. Thank you. And also thanks to Sol for helping us program the Arduino so we could get our puncturing mechanism work. And thank you to all of you guys for taking the time and listening to our presentation. If you have any questions, we are more than welcome. Thank you.
Right. We actually ahead of schedule, so we do have some time for a few questions. Um, if the audience have any, please feel free to unmute yourself and ask, or just type in the chat box. You are not able to speak through the microphone.
Yes, I do have a question. First off, I do want to say that was a great presentation, Sam Banjana. I liked it a lot. So thank y'all for doing that for us. My question is, I know that you said that your intention was to monitor the pressure and the temperature while the battery was being cycled. So I wanted to know if the device or if you all were able to do any charge and discharge cycles, and if so, were you able to measure any temperature or pressure changes with the device?
Jana, you want me to take this? We good?
Go right ahead.
Thank you. Well, we were not really allowed to have a real live battery inside the test chamber, just for safety purposes. But in the other hand, we were able to get some pressure readings. We were able to when we were testing our vacuum, we did get some pressure reading. We just couldn't keep that vacuum or the pressure inside the test chamber. I hope I answered your question.
Yes, thank you.
Yeah. So if you do the charging discharge, in this case will be a destructive test, which will need a very good safety, measurement in order, because battery may explode, may emit a gas. So you want to make sure it is controlled environment. So that's why the is beyond the scope of this current project, but definitely I think as a future work with collaboration with Naval Surface Warfare Center, they have a very comprehensive facility there doing all kinds of different battery safety testing, including the ones you just mentioned. So definitely that's could be the future work for maybe future senior capstone students. So any other questions, comments from the audience?
Samba, I know that we met previous week about some issues you had with sealing the system. Were you able to find some solutions to those issues?
No, actually, that's what I mentioned on the at the end, towards the end there. No, we got close, but we could not get the test chamber seal. And one of the main reason was that the surface of that resin when it cures is very rough, and we needed to find a way to smooth that off. And also the O rings, we could not get one that really worked, the right size or the right shape. Actually, no, unfortunately.
Very nice work, though, guys. I really enjoyed the presentation.
Thank you so much.
Yeah, so I guess I have a question that besides all all those challenges you have faced during your project, I wonder if you're given more time, you know uh, as part of your future work, how would you like to improve, or how what is your kind of plan, to further develop this, device you have designed.
Go ahead, John. I'll let you do this. Yeah.
Definitely, if we had more time, I mean, the vacuum seal would definitely be that would definitely be figured out if we had more time. That's one. If if we had time, if it was the possibility of testing an actual battery, if that was actually allowed, um, it would be through Dr. Hendricks and the Card Rock division if they would accept our project to be tested through their facilities. That's what we would think of. Something else.
Yeah, I just saw some comments coming through the chat. Nice presentation, great work. So I feel the same way. So congratulations for trying your best and finishing this project, under all these restrictions. Um, So any other questions before we move on to introduce our next presentation? And also, just remind everyone, please complete the survey for this group of presenters using the link in the chat box. Was there a question or some comments? I heard some. Okay.